Picture this. You're an archaeologist who spent decades building your career on a timeline that human civilization only became sophisticated after the end of the last ice age. Then, somehow, someone shows you evidence that advanced societies existed thousands of years earlier and were wiped out by a cosmic catastrophe. Do you embrace this paradigm-shattering discovery, or do you fight it to protect everything you've built your reputation on? Welcome aboard Arnie's Brain Train, where today we're going to be diving into one of the many scientific battles that's tearing archaeology apart. I'm Alex Arnold, and today we're investigating whether an asteroid impact 12,900 years ago destroyed advanced prehistoric civilizations, and why some scientists seem determined to bury this possibility. We're going to examine the evidence, the fierce resistance from academic orthodoxy, and what it means if researchers dismissed as fringe theorists have been right all along. All of my sources are listed in the description below, so you can dive even deeper after the journey. Here's the big deal. If this evidence is real, it doesn't just prove that cosmic impacts can cause climate chaos. It could prove that advanced human civilizations existed thousands of years before mainstream archaeology says they should have, and that some researchers who've been dismissed as fringe theorists might have been right all along. Buckle up, because this isn't just about ancient history, it's about how science really works when careers and reputations are on the line. Let's ride. In order to understand this catastrophe theory, we need to set our time machine to the end of the last ice age and really grasp what our world looked like back then. Picture Earth around 15,000 years ago. Massive glaciers covering much of North America and Europe, some reaching heights of over a mile thick. Woolly mammoths, giant ground sloths, and saber-toothed cats roamed vast grasslands that stretched from Alaska to Mexico. And scattered across this ice age landscape were early humans living in small groups, slowly developing the skills that would eventually build civilizations. Now here's where it gets interesting. The Ice Age wasn't ending gradually, like many of your textbooks have told you. Instead, around 14,700 years ago, temperatures shot up dramatically in what scientists call the Bowling-Allarod warming period. We're talking about temperature increases that would make modern climate scientists absolutely panic. Ice sheets were melting at breakneck speed, sea levels were rising rapidly, and life was flourishing in ways that hadn't been seen for thousands of years. Early humans were expanding their territories, developing new technologies, and here's where it gets controversial. Some researchers suggest they might have been building more sophisticated societies than mainstream archaeology has ever been willing to admit. These would be complex settlements, advanced toolmaking, possibly even monumental architecture. But more on that topic later. This is what the world looked like, and then, wham! Around 12,900 years ago, everything changed in what geologists call the Younger Dryas period. Named after a cold-living flower called Dryas octopetala that suddenly reappeared in the fossil record. This event plunged Earth back into near-glacial conditions for about 1,300 years. Temperatures in the North Atlantic region dropped by up to 15 degrees Fahrenheit in just a few decades. Let's just take a step back for a second to understand how rapid climate changes, like the Younger Dryas, helps us predict how our planet might respond to current climate shifts. If Earth's climate system can flip this dramatically this quickly, what does that mean for our future? Plus, this event coincides with major changes in human development. The end of the Clovis culture in North America, massive shifts in how our ancestors lived worldwide, and possibly the loss of an entire civilization that we're only now beginning to discover. Now back to our theory. For decades, scientists explained this dramatic cooling through something called the meltwater pulse hypothesis. Essentially, massive amounts of fresh water from melting glaciers disrupted ocean currents, particularly the Gulf Stream, causing rapid cooling. Picture it like throwing massive ice cubes into a perfectly balanced hot tub. Suddenly, the circulation gets all messed up. It was a neat, tidy explanation that most scientists accepted because it fit nicely into their understanding of how climate systems work. But then came a new group of researchers with a wild idea that would shake the foundations of multiple scientific disciplines. What if an asteroid or comet caused this chaos? What if the reason this climate change was so sudden, so dramatic, and so precisely timed wasn't because of natural ice sheet dynamics, but because something from space hit us so hard that it reset the entire planetary system? In 2007, a team led by nuclear chemist Richard Firestone dropped a scientific bombshell that would split the archaeological and geological communities right down the middle. They proposed that around 12,900 years ago, a fragmented comet or asteroid exploded in Earth's atmosphere and impacted across multiple locations, primarily over North America. But this isn't just another academic paper. This represented a direct challenge to decades of established thinking. Let's just think about this theory for a moment. We're not talking about one massive impact like the asteroid that killed the dinosaurs 66 million years ago. Instead, picture a cosmic shotgun blast, multiple fragments of a disintegrating comet or asteroid creating a chain of explosions and impacts across thousands of miles. The largest fragments might have hit the Laurentide ice sheet covering much of Canada and the northern United States, instantly vaporizing billions of tons of ice and sending massive amounts of water and debris into the atmosphere. The same team of researchers claimed that they found a black mat layer in sediment cores across North America, a thin dark layer of sediment that appears at exactly the right time period and contains some seriously unusual materials that shouldn't naturally occur on Earth's surface. But here's what really sent shockwaves through the academic world. If this evidence was legitimate, it meant that mainstream archaeology had been fundamentally wrong about the timeline and sophistication of prehistoric human civilizations. The hypothesis suggests that this cosmic bombardment had multiple devastating effects that read like something out of a disaster movie. It instantly melted portions of the ice sheet, creating massive floods that would dwarf anything in recorded history. The impacts and atmospheric explosions triggered continent-wide wildfires that turned vast regions into infernos. The debris thrown into the atmosphere blocked sunlight for months or years, causing rapid cooling and crop failures. And, perhaps most tragically, it may have contributed to the extinction of 35 genera of North American megafauna. Giant ground sloths, saber-toothed cats, American cheetahs, short-faced bears, and yes, those iconic woolly mammoths. But here's the human element that makes this theory so explosive and controversial. The timing coincides almost perfectly with the disappearance of the Clovis culture, some of the earliest well-documented peoples of North America. Were our ancestors witnesses to or victims of a cosmic catastrophe? And if entire human populations could be wiped out this quickly, what does that have to say about other potential civilizations that might have existed but left no trace? Now here's where we need to talk about something that doesn't get discussed enough in science communication. The intense resistance this hypothesis faced wasn't just about the evidence. It was about protecting established academic careers, funding streams, and entire theoretical frameworks that had been built over decades. Just think about it for 2 seconds. If you're a mainstream archaeologist who spent 30 years building your reputation on this idea that complex civilizations only emerged after the end of the last ice age, and suddenly someone suggests that advanced societies might have existed before a cosmic reset event, that's not just challenging your research, that's potentially invalidating your entire life's work. The original research team, which included archaeologists, geologists, and physicists, claimed that they had smoking gun evidence. But, as we'll see, the scientific community wasn't ready to accept such an extraordinary claim without extraordinary evidence, and some critics seemed determined to debunk it regardless of what the evidence showed. Alright, now this is where we're going to put on our detective hats and examine the evidence that's got scientists either jumping for joy or pulling their hair out. The impact hypothesis supporters claim that they've found multiple smoking guns buried in the geological record, and some of this evidence is so exotic it reads like science fiction. Let's break down their case piece by piece. First up, platinum spikes that shouldn't exist. Researchers found unusually high concentrations of platinum in sediment layers dating to exactly 12,900 years ago across multiple continents. Why is this such a big deal? Platinum is incredibly rare in Earth's crust. We're talking about concentrations measured in parts per billion, but it's relatively common in asteroids and comets. Finding sudden spikes of platinum in the geological record is like finding alien fingerprints at a crime scene. On Earth, platinum usually comes from deep mantle processes or volcanic activity, but the geographic distribution and timing of these spikes don't match any known volcanic events. The concentrations are sometimes 100 times higher than background levels, appearing suddenly in the geological record and then disappearing just as quickly. Our next one is a little more dramatic. They discovered nanodiamonds and tiny spherules of melted rock in the same black matte layer. Now, let me blow your mind here. Nanodiamonds can form under the extreme pressures and temperatures of cosmic impacts or atmospheric explosions. These aren't the kind of diamonds you'd put in jewelry. They're microscopic crystals that require incredibly violent conditions to form. Conditions that simply don't occur naturally on Earth's surface. The spherules, tiny balls of once melted rock, show signs of being formed at temperatures exceeding 2,000 degrees Celsius. That's hot enough to melt copper. These spherules contain unusual mineral assemblages and show rapid cooling patterns that the researchers argue could only form from the intense heat of cosmic impacts or massive wildfires triggered by atmospheric explosions. But here's what makes this evidence so compelling. The spherules contain microscopic inclusions of metals like iridium and osmium that are rare on Earth but common in space rocks. It's like finding cosmic DNA embedded in these tiny glass beads. This one really caught scientists' attention, and it makes this so much bigger than a local catastrophe. This evidence isn't just found in one location or even one continent. Researchers claim to have identified the black mat and its unusual contents across dozens of sites spanning from Alaska to South Carolina and even across the Atlantic in parts of Europe and the Middle East. If confirmed, this geographic distribution suggests a truly massive event, something on a scale of a global catastrophe that affected multiple continents simultaneously. We're not talking about a regional forest fire or a single meteor impact, but potentially multiple impacts or airbursts spread across thousands of miles. Impact supporters also point to shocked quartz. Quartz crystals that show unique fracture patterns called planar deformation features, PDFs, that are only created under the extreme pressures of cosmic impacts or nuclear explosions. These microscopic fracture patterns are like geological footprints that can't be faked or explained by normal Earth processes. They've also found high-temperature minerals like lonsdaleite, a rare form of diamond that typically forms during impact events, and stishovite, a high-pressure form of quartz that only occurs naturally in confirmed impact craters or locations where nuclear weapons have been detonated. Additionally, researchers have identified carbon spherules with unusual isotopic signatures and magnetic microspherules that show signs of being formed in high-temperature, low-oxygen environments. Exactly what you'd expect from massive wildfires triggered by cosmic impacts. These magnetic spherules contain metallic compositions that match extraterrestrial sources rather than terrestrial volcanic activity. Some contain microscopic inclusions of metallic iron with nickel concentrations that are diagnostic of meteoritic origin. Now, if you're wondering why any of this matters to your daily life or why we should care about microscopic diamonds and platinum spikes from 13,000 years ago, here's the thing. If this hypothesis is correct, it means that cosmic impacts aren't just ancient history. They're an ongoing threat to human civilization that we need to take seriously. Understanding how previous impacts affected climate and human societies helps us prepare for future cosmic encounters. We're learning that Earth exists in a cosmic shooting gallery, and major impact events might be more frequent than we previously thought. The research techniques being developed to study these ancient impacts are also advancing our ability to detect potentially hazardous asteroids and comets that might threaten our modern civilization today. But now hold on to your seats, because the scientific community has some serious problems with this evidence, and the resistance to accepting it reveals as much about the sociology of science as it does about the evidence itself. Remember how I said this hypothesis split the scientific community? Well, the pushback has been swift, thorough, and sometimes downright brutal. Critics argue that the Younger Dryas impact hypothesis is built on shaky foundations, and they've spent over a decade attempting to demolish the evidence piece by piece. But what's really fascinating is how this debate reveals the darker side of academic politics and the resistance to paradigm-shifting ideas. The biggest issue that critics raise? Other research teams have struggled to replicate the original findings. When scientists tried to find the same platinum spikes, nanodiamonds, and spherules at the claimed sites, many, not all, but many came up empty-handed. In science, if you can't reproduce results, that's supposed to be a major red flag that signals faulty methodology or contaminated samples. So here's what's interesting though. The impact hypothesis supporters argue that the replication failures are due to inadequate sampling techniques, different analytical methods, or simply looking in the wrong places. They point out that impact debris would be distributed unevenly across the landscape. So, not finding evidence at every location doesn't actually disprove the hypothesis. Dr. Andrew Scott from Royal Holloway University of London and his colleagues published devastating critiques, arguing that the supposed impact markers could be explained by much more mundane processes. They suggested that the nanodiamonds might be contamination from laboratory equipment, the spherules could form during natural wildfires, and the platinum spikes might result from changes in sedimentation rates rather than cosmic impacts. But let's be honest about what's really happening here. This isn't just dispassionate scientific debate. The impact hypothesis threatens fundamental assumptions that have guided archaeological and geological research for generations. If you've built your career on the idea that complex human societies only emerged gradually after the end of the Ice Age, the possibility of a cosmic reset event is professionally terrifying. Critics also continue to emphasize that we already have perfectly good explanations for the Younger Dryas cooling that don't require invoking cosmic catastrophes. The meltwater pulse hypothesis, where massive freshwater releases from melting glaciers disrupted ocean circulation, can account for the rapid climate change without needing asteroids. Why complicate things with exotic explanations when conventional mechanisms work just fine? Some researchers even argue that the megafauna extinctions were already underway due to human hunting pressure and climate changes at the end of the Ice Age. The timing correlation with the proposed impact might just be coincidence. After all, lots of things were happening at the end of the Pleistocene. Perhaps the most damning criticism, though, is where's the crater? The hypothesis proposes impacts large enough to trigger global climate change and continental-scale environmental destruction. Yet no clear impact crater from this time period has been definitively identified. Impact supporters suggest that the fragments mostly hit ice sheets that have since melted, or that atmospheric explosions, airbursts, left no craters, similar to the 1908 Tunguska event in Siberia that flattened 2,000 square kilometers of forest but left no crater. Critics find this explanation frustratingly convenient and argue that such massive impacts should leave some permanent geological signature. Here's the uncomfortable truth. Challenging established archaeological paradigms can be career suicide. Graduate students and early career researchers who show interest in fringe theories like the impact hypothesis often find themselves shut out of funding opportunities, unable to publish in top-tier journals, or simply unable to find academic positions. The scientific debate became so heated that some researchers published papers with titles like The Younger Dryas Impact Hypothesis, a Requiem, essentially declaring the theory dead and buried. But notice the language here. This isn't the dispassionate tone of scientific discourse, it's the triumphant declaration of victory in academic warfare. But the story doesn't end there, because science has a funny way of refusing to stay buried. Just when critics thought that they'd buried the impact hypothesis for good, supporters fired back with new evidence, improved methodologies, and some discoveries that have forced even the skeptics to take notice. This scientific back and forth has continued for over 15 years, and some recent findings have reignited the debate in ways that mainstream archaeology can no longer ignore. In 2018, researchers announced the discovery of a massive impact crater beneath the ice in northwest Greenland, called the Hiawatha Crater. This thing is huge, 31 kilometers across, and while the dating is still being refined, some estimates place it within the time frame that could be related to the Younger Dryas event. This discovery doesn't prove the impact hypothesis, but it does something even more important. It demonstrates that significant cosmic impacts did occur during the late Pleistocene period. Suddenly, the idea of cosmic impacts affecting human history doesn't seem quite so far-fetched to mainstream researchers. Recent studies have used more sophisticated dating techniques, electron microscopy, and analytical methods that weren't available when the original hypothesis was proposed. Some research teams claim that they've confirmed the presence of impact markers at additional sites across multiple continents, while others continue to find nothing. It's almost funny, but this debate has become increasingly technical, focusing on proper laboratory procedures, contamination controls, and statistical analysis. The crude dismissals of the early criticism have given way to more nuanced discussions about methodology and interpretation. Some researchers are now pointing to archaeological evidence from sites like Tal el Haman in Jordan, where they claim to have found evidence of a cosmic airburst around 3,600 years ago that destroyed a Bronze Age city. While this is much more recent than the Younger Dryas, it demonstrates that significant cosmic events have affected human civilizations throughout history, and that the archaeological record might contain evidence of multiple cosmic catastrophes. Here's why this whole debate is more than just about what happened 12,900 years ago. This research is advancing our understanding of cosmic threats, improving our analytical techniques for detecting ancient impacts, and helping us better understand how climate systems respond to sudden disruptions. Whether the impact hypothesis is ultimately proven or disproven, the scientific process itself is making us smarter about our planet's history and our cosmic neighborhood. We're developing better ways to identify impact signatures, more sophisticated climate models, and a deeper appreciation for how quickly planetary systems can change. The truth is, science is messy and political. Revolutionary ideas often face fierce resistance before being accepted or ultimately rejected. The impact hypothesis remains one of the most controversial topics in archaeology and climate science, with passionate advocates and critics continuing to duke it out in peer-reviewed journals. Now let's talk about the part that really has mainstream archaeology scared and why they don't want to talk about it. The implications of the Younger Dryas impact hypothesis for our understanding of prehistoric human civilizations. If this hypothesis is correct, it doesn't just rewrite climate history, it potentially validates some of the most controversial ideas in archaeology, and forces the academic establishment to confront an uncomfortable truth. So here's the scenario. What if sophisticated human civilizations existed before the Younger Dryas impact, and the cosmic catastrophe essentially reset human cultural development? What if the reason we don't have clear archaeological evidence of advanced prehistoric societies isn't because they didn't exist, but because a cosmic catastrophe wiped them out so completely that only fragments of their achievements survived? Think about this logically. If a cosmic impact could trigger continent-wide wildfires, massive flooding, and a 1,000-year climate catastrophe, it could easily destroy most traces of wooden structures, organic materials, and even stone constructions. The survivors would have been too busy staying alive to maintain libraries, technical knowledge, or monumental architecture. This whole concept isn't just a theoretical speculation. We know from historical examples that civilizations can lose complex knowledge remarkably quick. The fall of the Roman Empire led to the loss of concrete technology for over 1,000 years. The Library of Alexandria's destruction eliminated countless works of ancient knowledge. Now imagine a catastrophe thousands of times more devastating. Researchers like Graham Hancock, for example, who have long argued for the existence of sophisticated prehistoric civilizations, have been dismissed by academic orthodoxy as pseudoscientists and fringe theorists. They've been denied platforms at academic conferences, had their work excluded from peer-reviewed journals, and faced professional ridicule for suggesting that human civilization might be much older and more sophisticated than currently accepted. But if the Younger Dryas impact hypothesis is correct, some of these so-called fringe researchers might have been onto something all along. The timing of the proposed impact coincides perfectly with Hancock's suggested timeframe for an advanced prehistoric civilization that was destroyed by a global catastrophe. Here's another dirty little secret of academia. Institutions are incredibly resistant to paradigm shifts that threaten established power structures. Professors who have built entire careers on specific interpretations of human history don't just disagree with revolutionary new ideas, they actively work to suppress them because acceptance would mean admitting that they've been fundamentally wrong for decades. The resistance to the impact hypothesis is barely about the evidence at all. It's about protecting academic territories, research funding, and professional reputations. If mainstream archaeology has to acknowledge that they dismissed legitimate researchers as pseudoscientists, it raises uncomfortable questions about the objectivity and openness of the entire field. Just as a side note, Göbekli Tepe was first discovered in the 1960s, and then dating was established in the 90s. Why is it that we didn't get its first publications until 2013? What if Göbekli Tepe isn't the beginning of sophisticated human architecture, but rather one of the few surviving examples from a much longer tradition that was largely wiped out by the cosmic catastrophe? What if the people who built Göbekli Tepe were survivors of a more advanced civilization, trying to preserve and rebuild their lost knowledge? Across the world, we find massive stone structures that mainstream archaeology still struggles to explain. Perfectly fitted polygonal walls in Peru, massive stone circles in Turkey, precisely aligned monuments that demonstrate sophisticated astronomical knowledge. The current archaeological timeline suggests that these represent the sudden emergence of complex societies. But what if they actually represent the rebuilding efforts of survivors from a cosmic catastrophe? If you were a survivor from an event such as this that destroyed most of human civilization, how would you preserve essential knowledge for future generations? You might encode it in myths and stories, build massive stone monuments that could survive future catastrophes, and maybe even develop systems for passing down critical information through oral traditions. This could explain why there are over 200 flood myths found in cultures across the globe, why megalithic structures show similar construction techniques on different continents, and why ancient astronomical knowledge seems far more sophisticated than we'd expect from supposedly primitive peoples. If the impact hypothesis gains wider acceptance, mainstream archaeology will face a reckoning unlike anything that the field has ever experienced. They'll have to acknowledge that they dismissed legitimate researchers, suppressed alternative theories, and potentially set back our understanding of human history by decades through their resistance to paradigm-changing ideas. Most importantly, they'll have to admit that human civilization might be far more resilient, ancient, and sophisticated than current textbooks suggest, and that our ancestors survived and recovered from catastrophes that would challenge even our modern technological society. Alright guys, it's been a long one, but let's bring this wild journey full circle. We've traveled from cosmic catastrophes to microscopic diamonds, from ancient ice sheets to modern academic politics, and uncovered a scientific controversy that could fundamentally reshape our understanding of human history. On one side, we have impact hypothesis supporters pointing to platinum spikes, nanodiamonds, shocked quartz, high-temperature spherules, and geographic distribution patterns that they argue can only be explained by cosmic impacts. The evidence spans multiple continents and involves exotic materials that are difficult to explain through conventional geological processes. On the other side, we have critics who've struggled to replicate these findings and offer alternative explanations for each piece of supposed evidence. They point to the lack of definitive impact craters, problems with laboratory contamination, and the availability of conventional explanations for the younger Dryas cooling. But what makes this debate so much bigger is that it's fundamentally about how we understand the relationship between cosmic events and human history. If the impact hypothesis is correct, it suggests that human development has been periodically reset by cosmic catastrophes, that we might have lost entire chapters of our story to asteroid impacts and comet explosions. That would also mean that researchers like Hancock, who have argued for sophisticated prehistoric civilizations, might have been correct all along. It would force mainstream archaeology to confront the possibility that they've been wrong about the timeline and sophistication of human societies, and that they've unfairly dismissed legitimate researchers as pseudoscientists. The fierce resistance to the impact hypothesis reveals so much about modern science. Academic institutions are notoriously resistant to paradigm shifts that threaten established power structures and research paradigms. The stakes aren't just about interpreting ancient history, they're about careers, funding, and the professional credibility of entire fields of study. This is so much more than just ancient history. Understanding how these impacts affect climate, ecosystems, and human societies is crucial as we face our own environmental challenges and potential cosmic threats. The research techniques developed during this debate, methods for detecting ancient impacts, understanding rapid climate change, and analyzing microscopic evidence, are advancing our scientific capabilities across multiple fields. We're truly starting to understand the cosmic shooting gallery that Earth lives in, and that the story of human civilization might be far more fragile and far more interrupted than we ever imagined. This knowledge is essential for developing planetary defense systems and understanding how quickly our own technological civilization could be disrupted and ended by cosmic events. Perhaps most importantly, this controversy demonstrates both the best and the worst aspects of the scientific process. We're watching hypothesis formation, evidence gathering, peer review, criticism, and revision in real time. Whether the impact hypothesis ultimately survives or falls, the process of testing it rigorously is making us smarter about our planet and our place in the cosmos. This hypothesis reminds us that science is not a collection of fixed facts, but an ongoing process of discovery that sometimes requires us to fundamentally reconsider everything that we thought we knew. Well, everybody, that's where we'll park the brain train for today. We've journeyed through cosmic catastrophes and microscopic evidence, from ancient civilizations to modern scientific debates, and discovered that the question, did an asteroid wipe out an advanced prehistoric civilization, might have a more complicated answer than we ever imagined. The evidence for a cosmic catastrophe 12,900 years ago remains hotly debated, but it's forced us to confront uncomfortable questions about what we really know about our prehistoric past. Whether advanced civilizations were wiped out by cosmic impacts or not, the possibility has opened our minds to just how much of human history might still be waiting to be discovered. If this evidence proves that advanced civilizations were destroyed by cosmic impacts, it means that some researchers who have been dismissed as fringe theorists might have been onto something all along, and that mainstream archaeology might have to do some serious soul-searching about how they've treated alternative perspectives on human history. But what do you think? Does the evidence convince you that an asteroid wiped out an advanced prehistoric civilization? Or do you side with the critics? Do you think mainstream archaeology has been too resistant to considering the possibility of sophisticated ancient societies? And what would it mean for our understanding of human history if cosmic catastrophes have repeatedly reset human civilization? Drop your thoughts in the comments below. I love hearing from fellow curious minds who aren't afraid to question established thinking. As usual, all of the scientific sources that we've discussed today are listed in the description, so you can continue this incredible journey of discovery and form your own conclusions about this fascinating controversy. And if your brain is buzzing with new knowledge and questions about the hidden history of human civilization, smash that subscribe button and ring the notification bell. We've got more mind-blowing mysteries coming your way every week. From ancient civilizations to cosmic wonders, there's always another adventure waiting aboard Arnie's brain train. Until next time, keep asking, but why? And never stop questioning what you've been told is settled science. Because the world isn't always this simple, but it's always this interesting. We'll see you guys next time. Bye.